Hello, good evening. Tonight I'm going to be talking a little bit about muscle contractions with skeletal and smooth muscle. And just to start off, I want to start talking about the sarcomere and what it looks like, what's going on the molecular level. So the sarcomere um, is there's going to be sarcomeres in every muscle cell, and they're going to have little striations here. Um, and these striations are going to be our filaments that are going to allow for muscle contraction. So what I'm drawing here is we've got some thin filaments. So this is one sarcomere. Here we have our thick filaments, and we have our thin filaments. And just to zoom in a little bit on what's going on in both of these, so our thick filaments are made up of something we call myosin. Myosin has two heads like this, and it has two interweaving tails behind it. And myosin up here up top, it's got two actin binding sites. It also has a binding site for ATP. And using these two binding sites, it's going to be able to go into what we call cocked and uncocked position, which I'll go over in a sec, and that's going to ultimately lead to muscle contraction as the myosin heads slide back and forth with the thin filaments here. So just to give a little example, we've got all these little myosin heads all around the sarcomere, or all around the thick filament, and these are going to connect to the thin filament and contract and pull the thin filament this way, and that's what's going to cause our muscle contraction. Now, what does the thin filament actually look like? The thin filament is going to be made up of what we call G actin proteins. That's what these little circles are I'm drawing. Each one of these is a G actin protein, and the chain itself is an F active protein. So these G actin proteins are going to kind of go in a helical shape around another protein we call nebulin. The nebulin is going to be connected to this actin through titin, and that's what's going to be able to reset the muscle fibers after a contraction. Um, and this G actin is not going to just be open. It's actually going to be covered by something called tropomyosin. So the tropomyosin is going to be covering all of these active binding sites because, again, the actin binding site, or the myosin here has actin binding sites. So it's going to want to bind to our actin right here and be able to do contractions on it. But this tropomyosin is going to kind of be regulating that, covering those actin sites. And we have another protein called troponin, which is going to decide when the tropomyosin gets removed from the actin. Oops. So if we blow up the troponin, it has three little circles, kind of like Mickey Mouse, and it's got a C, I, and T site. The C site is going to be a calcium binding site, so calcium is going to be very important in muscle contraction. The I is going to be actin binding site, so that's going to be binding to the actual blue circles here. And then the T is going to be binding to tropomyosin, and that's what's actually going to be lifting the tropomyosin off of the actin so that the myosin head is able to bind to the actin. So that's kind of what's going on a molecular level of both of those, the um, the thin and thick filaments. It's all about myosin binding to that actin. And how this works in a cell, in a muscle cell. So we have our muscle cell right here. We've got a T tubule there, and we have a neuron coming down. And what's going to happen is when a signal is sent down, there's going to be an action potential, a Wong coming. And what's going to happen is that's going to allow calcium to come into the cell. We have our vesicles here full of acetylcholine, and our snare proteins are going to let that acetylcholine get out into this synapse here. We have some acetylcholine receptors here. Those are going to be binded to. It's going to cause opening of a sodium potassium ligand channel, and what's going to happen there is sodium is going to want to come in, potassium is going to leave, but much more sodium is going to be coming in, which is going to also trigger another sodium voltage gate to open, allowing more sodium to come in. That's ultimately going to be causing an action potential inside the muscle cell. And what happens during an action potential? So I'm going to draw on the other side here. Next to this T tubule that we have here, this invagination of the muscle cell, we have next to it something called the sarcoplasmic reticulum. The sarcoplasmic reticulum has a lot of calcium inside, which, as we just looked at, we are going to need calcium to have any binding of the myosin to the actin. So the calcium is stored inside here, and the way that it's going to get out is the sarcoplasmic reticulum has a channel called RYR, and then there's also on this T tubule a channel called DHP. So when an action potential happens, what's going to happen is the RYR and DHP are going to both, sorry, let me zoom in here, are going to both be able to open. And when that happens, because there's such a low concentration of calcium in the ICF, and there's a high concentration of calcium in the ECF, it's high there, but it's low here, high here. What's going to happen is calcium is going to rush into the ICF. And as that happens, calcium is going to be binding to the C actin, or the C troponin, sorry, and that's going to allow for myosin to be able to bond to our actin filaments here. So let me just draw that out on a molecular level here. So here, let's say we have our thin filament, we have our actin here, and we have our myosin here. The myosin is going to start out with an ADP and a phosphate on it, and we call this cocked position. This is myosin. What's going to happen is this is called a cross bridge cycle. So calcium has just increased in the ICF. Calcium comes in, and what happens is the actin is now available for the myosin to bind to. So the myosin head is going to get up onto this actin. Still got that ADP on it and the phosphate. And when that bond is created, what's going to happen is heat is going to be released, and the ADP, so the heat's going to come off here, and that's going to cause the ADP and the phosphate group to be pushed off of that myosin. And what's going to happen next is the myosin will stay binded to the actin, but it's going to uncock here. So we call this uncocked. And when that power surge happens, this is going to be pulling, let me get out my, this is going to be pulling the edge of the sarcomere closer to the center of the sarcomere. So these edges on the left and right are going to be pulled towards the middle, and that's what a muscle contraction is. So when that happens, we have a muscle contraction. And for the myosin to be able to unbind so that we can rest, we're going to get some ATP that comes in here. It's going to bind to that ATP binding site on our myosin head, and that heat from the ATP bond is going to break the myosin off. It's going to stay cocked. It's going to break the myosin off of the actin, and it now has this ATP. And then to restart it all, we have hydrolysis. So the ATP is going to go and become an ADP, and that extra phosphate is going to be put in the position. So we're going to recock our myosin. And this can be happening in multiple times in one muscle contraction. So this cycle is going to kind of happen over and over, so we can get the sarcomeres as close to each other, the edges of the sarcomeres as close to the middle as possible, and in an entire muscle, not every single muscle fiber is going to be in the same exact spot of this cycle, which is going to help with contraction of the entire muscle. Some of the energy sources. Let's talk about energy for muscle contraction. Well, there's not any energy source that's more important than ATP. For us to be able to have a contraction and then a unbind and us be able to have another contraction, we need ATP. And there's a couple ways that we can get ATP. There's cytosolic ATP. So that's just floating around in the cytosol of the cell. So the cell can basically just find some random ATP that's floating around and use it to do some contractions. Usually that's only going to last us a couple of seconds, though. The next way that we can get ATP is through a molecule called creatine phosphate. And this molecule is going to come by and be able to phosphorylate ADP and turn it into ATP so it can be used in another round of contractions. That should buy us a couple more seconds, maybe around 10, 20 seconds. Another way that we can get more ATP for more contractions is glycolysis. Now, glycolysis is anaerobic respiration. And what anaerobic means is without oxygen. So glycolysis is the breakdown of glucose within the cell, and it creates ATP. And so that extra ATP that we get from glucose is going to give us another 30 seconds to a minute of contractions that we can be able to do. Still not too much. And you might be wondering up to this point, how is it that we can stand for hours or walk for hours and we're flexing muscles? We're contracting our skeletal muscles for extended periods of time if we can only have enough ATP for 30 seconds. And the answer to that is aerobic ATP. So aerobic means with oxygen, and this ATP is going to come as oxygen is flows into the bloodstream and diffuses into the cell, and then is used by the mitochondria to create more ATP. This is a great option because it's going to allow for muscle contractions that last for multiple hours for a long time. The only downside of aerobic ATP is that it's too slow for any explosive muscle movement. So we can't just go off of aerobic ATP to, I don't know, do something like a bench press or bicep curls in the gym. It's going to be more for stuff like running, walking, um, standing, anything like that. And those are our number one ways that we're going to be able to get ATP and be able to run these cycles. Now, when it comes to smooth muscle, there's some similarities and some differences. So the smooth muscle is also going to have those sarcomeres. There's actually two different types of smooth muscle that we want to talk about. The first one is called single unit smooth muscle. And single unit smooth muscle is going to be bound together by what we call gap junctions. So every muscle fiber cell is going to be bound to the next one by gap junctions, and because of that, they're going to be able to do unified contractions. So, for example, kind of like contractions in the stomach where it kind of goes in waves, or contractions in the intestines. These are going to be single unit um, smooth muscle. The other kind is going to be called multi-unit. These smooth muscle are going to rely not on each other, but just on themselves. So they're going to fire all individually. The downside of this is that multi-unit smooth muscle is going to rely on stimulation from the spinal cord or the nervous system to be able to contract. Meanwhile, the single unit smooth muscle is going to be able to continue contracting, continue functioning without any input from the central nervous system, from the nervous system. So if you put your stomach in the right solution, it would continue functioning without any um, help from the brain. An example of multi-unit would probably be something like your iris in your eyes. Um, that's going to rely completely on stimulus from the brain to be able to react. And the way that smooth muscle contracts, there's two different types. The first is called phasic. So what's going to happen here, it's kind of similar to our skeletal muscle. You're going to start out with our actin and our myosin, and we'll still have our ADP and our phosphate. The only difference here is that the actin is not going to have any tropomyosin on it, not going to have any troponin on it. The way that myosin is going to be able to bind to the actin in this case is through an extra phosphate group that we're going to pick up here in a second. So if we go to our next step, the myosin is actually going to pick up another phosphate group and be able to bind. So it's going to pick up this second phosphate group, and that's going to come from something called MLCK. Now, when an action potential occurs in a smooth muscle cell, just like the skeletal muscle cell, the intracellular calcium concentration is going to increase. That calcium is going to bind to something called calmodulin, which has 4 binding sites for calcium. Once those binding sites are taken up, it's going to be able to excite the MLCK. So let's say MLCK kind of looks like a snake trying to eat its tail. That's the inhibited position. The calmodulin comes in and the MLCK straightens out and is now able to phosphorylate our myosin. So let's say the calmodulin's right here. So the MLCK is going to come in here and it's going to be able to phosphorylate that myosin right there. Because of that extra phosphate, the ADP is going to be able to make a bond with the actin, or not the ADP, sorry, the myosin head is going to be able to make a bond with the actin. And that bond is going to release some heat, and it's going to cause our original ADP and phosphate groups to fall off. And that's going to cause a cocked, or an uncocked, sorry. That's going to cause us to go into an uncocked position, just like we saw above with skeletal muscle. The only difference is we're still going to have this phosphate group on the myosin. What's going to happen next is the ATP is going to come in and bind to that myosin. That's going to enable the myosin to detach from the actin. We're still going to have that phosphate on there, but now we have our new ATP. And then the last step is the ATP will be hydrolyzed. But not only that, something is going to happen here so that we can get rid of our extra phosphate group. And that is going to be removed by something called MLCP. Now, MLCP is going to come in and take off that phosphate group for us. But that is only if it is not being inhibited by something called Rho kinase. So if Rho kinase is being inhibited, then it will not inhibit MLCP, but usually it is not being inhibited, so Rho kinase is going to stop MLCP, usually from taking this phosphate off. So what we're going to do is actually a lot of times skip that first step and come over here and be able to hydrolyze that ATP and go back to having an ADP and the double phosphates. So that's going to be our usual route for phasic, which means the smooth muscle is contracting, relaxing, contracting, relaxing in a pattern-like way. The next kind is tonic, which is similar. So we're going to start here. our ADP, our phosphate group, and we're going to have the same first step as before. So the MLCK is going to come in. It's going to give us another phosphate. It's going to let us bind the myosin to the actin. ADP, we got our phosphate, and we got our new phosphate that came from the MLCK. That's going to cause us to go into the uncocked position, but another change in isotonic versus, or in the tonic versus phasic is that the MLCP that came in the earlier step is actually going to come in even earlier, and that's going to come in and it's going to remove that extra phosphate. So the ADP is removed, the phosphate group is removed, and then the extra phosphate group is also removed. And so what's going to happen here is we're going to have a step called latch. So the smooth muscle cell is stuck in contraction. And basically ATP in our other process is going to come in and help the myosin to unbind from the actin. But in this case, the ATP comes in and it has a really hard time binding with the myosin. So it's going to take a lot longer for that to happen. And this is really useful in like sphincters. Obviously, we don't want those opening up just whenever. So it's nice that those cells are able to stay contracted longer. Eventually, that ATP is going to be able to bind onto oh, sorry, I drew it connected. Eventually, ATP is going to be able to bind onto it and help us to get our myosin off of the actin. And then our same step of hydrolysis is going to get us from the ATP to the ADP and the phosphate group. So slightly different there for the tonic versus the phasic. So just a couple comparisons and contrasts between smooth and skeletal muscle. So the smooth muscle is not going to have the striations like skeletal muscle will, but they're both going to have those sarcomeres. One difference is that smooth muscle is actually able to contract 80% of its length, whereas skeletal muscle only 30%. Smooth muscle is going to be able, it's definitely going to contract slower, but it's going to be able to be more powerful. I don't know how to spell. More powerful, and be able to do it for a lot longer time than the skeletal muscle. And finally, I just want to explain a little bit about the muscle sensory receptors, muscle spindles. So if we draw a muscle out here, the muscle is going to have two different kinds of things in here. Sorry, 1 second. It's going to have two different kinds of fibers inside of it that are going to help the brain know what length the muscle is. So we're going to have our intrafusal fiber or chain fiber. And then over here we're going to have our bag So it's also called intrafusive fiber, but this is going to be our bag fiber. And so what both of these are going to do is they're going to be stretch receptors. Let me write that down. So the bag and the chain fibers are going to report to the brain different things about how much our muscles are stretching and what to do in response to that stretch. So, for example, with intrafusial fibers, you're going to be feeling a lot of sensitivity from the intrafusal during stretching. So, intrafusal is during stretch, but once stretching has stopped changing, or sorry, during change in stretch. Once the muscle has stopped stretching, you're going to stop feeling, the intrafusal is not going to be able to tell anything. So if there's no change, then the chain can't tell. The bag fiber is going to be less receptive when there's change, but during extended stretching. So if we're just sitting here and say I draw an arm. So we're just sitting here in our flex state. The bag fiber is going to be good at detecting that we're in a flex state, but it's not as good at detecting the change. Muscle spindles versus Golgi tendon. So on our tendons, there's going to be these things called the Golgi tendon organs. Those are going to monitor whether our muscles are actually doing damage to our bones. So our muscles are actually strong enough to break every bone in our body. So if our muscles start to stretch too much or start to contract too hard, the Golgi is going to send um, an inhibitory stimulus to the muscle that is contracting, and it's going to send a excitatory signal to the muscle that is resting or stretching. And how that differs from the withdrawal reflex. The withdrawal reflex is where we are going to, for example, if there is a hot stove and you put your hand out to touch it, it's a terrible hand. But we've got our arm here. What's going to happen is if you touch it, the muscles in your bicep, what's going to happen is these neurons right here, these sensory neurons, are going to send a synapse all the way back to the spinal cord. They're going to come here, synapse, and then they're going to send a message back to the arm, to your bicep, to contract, to get your hand up and away from that hot surface. So that's kind of how our reflexes work within our body. Your brain is also going to receive word anytime that there is any reflex that happens. The brain is going to be notified of it, and the brain ultimately has overriding power over any reflex. But yeah, that is about all I have for tonight. Thank you very much for listening, and I hope you have a great night. Thank you very much.